Hello everyone, today we are going to develop a hydrostatics problem. Specifically manometry, which corresponds to the fluid mechanics book by Junis Singal, 4th edition. The problem says, consider a double fluid manometer. Here we have double fluid, one in purple and one in yellow. Attached to an air pipe is shown in the figure. This manometer is attached to this pipe that contains air. If the specific gravity of one of the fluids is 13.55, the figure tells me that it is the purple liquid that its specific gravity is 13.55, which tells us that this must be mercury. Determine the specific gravity of the other fluid, that is, the yellow one, for the indicated absolute air pressure. So, what the problem is telling me is that the pressure that is here is absolute pressure. The one that is inside this enclosure. Consider that the atmospheric pressure, ATHICS, is 100 kPa or 10,000 pascals. We know from theory that absolute pressure is equal to gauge pressure plus atmospheric pressure, and in this case they are telling me that atmospheric pressure is equal to 100,000 pascals. Let's leave it at 100 kPa. Having this clear and knowing that the pressure here is the absolute pressure, we can calculate the gauge pressure at this point, and we also know that the gauge pressure here comes to be 0 pascals. For what reason? Because it is in contact with the environment, therefore, the gauge pressure of the air will be equal to what? The absolute pressure, which comes to be 76 kPa minus the 100,000 pascal that are here. That is, from this equation we are simply clearing the gauge pressure, which would be the following. It would be 76 kPa minus 100 kPa, with which I would be left with that gauge pressure would be 24 kPa with a negative sign. That would be the gauge pressure. Within this point, it is with this gauge pressure that we are going to raise our manometry equation, since we have the pressure of 0 pascals here. Now the next thing we have to know by theory is that in this entire enclosure, since it is a gas, the pressure is the same. That is to say that here it is 76 kPa as absolute pressure or 24 Pascal as negative pressure. In all these points that pressure, it's going to be exactly the same here as at the interface with the liquid, which has a specific gravity of 13.55. Why? Because all of this is a gas. When it's a gas, the pressure is the same throughout the volume. Now we are going to set up our equation. The pressure that is here is the same as the air pressure, and we set up the equation in the following way. The air pressure, which is this pressure that is here, plus, as this is descending, when it descends the pressure increases up to this point. It would be plus the density of what liquid, of this liquid here, which in this case is mercury. We are going to put mercury here multiplied by gravity multiplied by height. How much is the height and depth? In this case it is 22 centimeters, which would be 0.22 meters. Remember that I have to work in the international system, and for that reason I automatically convert it to meters. As this point and this point are the same height, it means that the pressures are exactly the same. Automatically I go here, and from this point I am going to go to this point here. When I go up the pressure decreases, for that reason here it would be less. Less density of what fluid? Density of this yellow liquid fluid. That I don't know. I'm going to put density of 2 multiplied by gravity multiplied by the height or depth, which in this case is 33 centimeters or 0.33. This has to be equal. This has to be equal to 0 pascals, which is the gauge pressure. All the pressures we are working with here are gauge. Very well, now this air pressure, which is the gauge pressure we already calculated previously. which is minus 24 Pascal, what we are going to do is simply replace. Here it would be minus 24 Pascal plus the density of mercury, as this is the specific gravity. We know that the specific gravity is equal to the density of a fluid over the density of water at 4 degrees Celsius, and this density corresponds to 1. Which means that the density of that fluid, which in this case is mercury, is going to be equal to 13.55 per thousand, which would be 13,550 kilograms per meter cubic, which we replace here the density of mercury, which is this density of the fluid would be 13,550 multiplied by G, which is the gravity 9.81 multiplied by 0.22 minus, or this minus sign would go to the other side as a sum. Let's put equal. Here it would be the density of that second liquid that I don't know multiplied by 981 multiplied by 0.33 ready. My only unknown is this density of 2. Solving and replacing, we will have the following. It would be that the density of 2 is going to be equal to 1619 kilograms per cubic meter. But what are they asking me? They are asking me to determine the gravity specific, and what is the specific gravity equal to? It is equal to the density of the fluid, which in this case is the density of fluid 2 over the density of water at 4 degrees Celsius. Since the density of the fluid is 1600.19 and the density of water is 1, this means that the specific gravity of that second liquid that I don't know is going to be equal to 1.61.9 without units. Since here the units of the densities are eliminated, which would be the answer to the problem, it is a fairly simple problem. You had to take into account the data of the absolute pressure and the atmospheric pressure. If you have any questions or queries, please do so in the comments. Greetings all.